What we're going to do now is to review and revisit the transmission line equations, but this time with our newfound knowledge of phasors. So before we do that, let's start by reviewing the transmission line equations, mostly because in the past we had assumed lossless conditions. So I want to re-examine these equations without that assumption and go back to the basic telegrapher's equation before we apply phasors. So recall that for a very small unit length, we model the effects with a series inductor and resistive loss, as well as a shunt capacitor and a shunt resistor loss, where in this case we use conductance instead of resistance, so G, which is 1 over R. And the main purpose for that is that if we wanted to assume lossless, we just assume R and G are equal to 0. So there's no one is 0, the other is infinity, or anything like that to keep track of. And also remember that this is a short segment of length, so all of these are in units of ohms per meter or henries per meter. And so there's a little delta Z here. Now if we apply, I won't go over into it in as much detail as before, but if you use Kirchhoff's voltage law here and Kirchhoff's current law at this node, you end up with the two basic equations that we start out with. So dV dz is going to be equal to minus Ri minus L di dt. And then the other equation, using Kirchhoff's current law, you'll get di dz is going to be equal to minus GV minus C dV dt. Now one thing to note is that in the past I used lowercase I. Right now I'm switching over to uppercase I. The main reason for that is that we did a textbook change, and I think that changing the convention to go along with it will make comparing this with the book a little bit easier. So for those of you that aren't using either of the books, please bear with me. So these are the basic telegrapher's equations. We'll refer to these as equations 1 and equations 2. And then next up, what we're going to do is we're going to do some substitutions and some manipulations so that you see this is an equation of V and I. Here is a first order equation of I as well as V. And what we're going to do is we're just going to convert this into a second order differential equation that's either all voltage or all current. So in general, what we do is we take d by dz of 1 and d by dt of 2, and then substitute the result in. So if you do that, you get the first equation that we're going to work with. So d by dz squared of v is going to be equal to lc d by dt squared of v plus lg plus rc d by dt v plus rg v. And then similarly, if you take d by dz of 2 and d by dt of 1 and do a substitution, you're going to end up with a similar equation for the current. So the second derivative with respect to z of I is going to be equal to lc d by dt squared I plus lg plus rc of d by dt of I plus rgi. So I'm going to call this equation 3 and this equation 4. So these are the basic transmission lines equations, and what we're going to do next is re-examine them through the perspective of phasors. Now let's take a look at what solving these differential equations look like if we are looking at it through the lens of phasors. So again, the key equations, there's a set of 2 equations that I'll be looking at later over here. And then separately also, we're going to start out by looking at these two over here. So let's start with our inputs. We're gonna look primarily at the voltage. So remember we did a slight variation on the forward-backward propagating wave, where before we were just talking about it as general functions of, in the case of forward propagating waves, t minus z over vp, and backward propagating wave would be t plus vp. In this case, we're specifying that they're sinusoids. So that would be an amplitude cosine and then omega t minus z over vp plus wave going in the negative z direction, which will be v naught cosine of omega t plus z over vp. So if we distribute the omega inside, we end up with the instantaneous form of our input that we're putting into this equation. So that's going to be v of zt is going to be equal to v naught cosine of omega t minus beta z plus v naught cosine of omega t plus beta z. And recall that beta is going to be equal to omega over vp, or also commonly 2 pi over lambda. And remember, I defined beta as where omega is in radians per second. So how many radians of phase occurs for every second? Beta is the spatial equivalent of that. So it's in radians per meter, or how many radians pass by if you if you look forward in the wave by 1 meter. Now let's convert this into Phasor form. So the first step is to expand it into the real part of a vector in the real complex plane. So we're going to rewrite this as the real part of v naught, and I'm going to shift the beta z to the beginning. So j beta z e to the j omega t plus v naught e to the plus j beta z e to the j omega t. So as a quick review, what we mean by phasor analysis is that we only focus on the complex amplitude. Here we forget about the e to the j omega t and taking of the real part, do our analysis, and then once we're all done, we convert back to the instantaneous form by multiplying it by e to the j omega t and taking the real part. So a forward propagating wave would be, we'll call this v naught. S is referring to the fact that it's a phasor, plus to indicate that it's a forward propagating wave, and now it's only a function of z because we're going to ignore the e to the j omega t part. So the representation for forward propagating wave would be v naught e to the minus j beta z, and a wave propagating in the negative z direction will be v naught e to the plus j beta z. Now, if we were to take this equation and put it into equations 3 and 4, one important thing to note is that when you're working with phasors, the only time-dependent term is this e to the j omega t. And therefore, if you take d by dt of a phasor, that will be the same as multiplying it by j omega. So that's the main adjustment that we're going to make when we put it in here, is that now when we see d by dt, we're just going to multiply it by a factor of j omega. So applying this to equation 3, so we're going to stick this expression in here, and what we're going to get is d by dz squared vs, so that we add the s because now it's a phasor, is going to be equal to LC second derivative with respect to Vs plus Lg plus Rc first derivative with respect to S plus Rg Vs. So all I did was I took equation 3 and I added a subscript s. Just take it one step at a time. Now I'm going to substitute d by dt with multiplying it by j omega. So d by dz squared vs is going to be equal to minus omega squared lc vs. And then plus, so this is a minus because we're taking j omega squared, and j squared is equal to -1, plus j omega of lg plus rc vs plus rg vs. So one of the things that you'll see is that you can factor out the vs, and with what's left in here, people that are more clever than me can immediately see that you can actually factor this out as a polynomial into r plus j omega l and g plus j omega c vs. So you can also prove that to yourself. If you multiply this out, you're going to get this equation. So what we're going to end up doing is then, if we just call this whole thing gamma squared, you can write this whole thing as d by dz squared vs is going to be equal to gamma squared vs, where gamma is going to be equal to the square root of all this stuff over here. So r plus j omega l, g plus j omega c, square root. So this is another key outcome that I want us to remember. Now, if you take a look at this, these are just complex numbers, and then you take the square root, the result is still going to be a complex number. So whatever it is, you should be able to separate it out into a real part and a complex part, which I'm just going to call alpha, and then I'm going to call the complex part j beta. So that is ultimately how we're going to view this gamma, even though if we actually needed to find it, we would calculate in terms of r and l and g and c using this equation up here. So now I'm going to use this half of the board here, and let's plug this result in and find the instantaneous form. So rewriting based on this result here, we can see that the total solution of the phasor with both positive and negative components will look like e to the minus, the positive traveling component is going to be e to the minus gamma z, and then the negative traveling wave component is going to be e to the plus gamma z. So if we rewrite gamma as just alpha plus j beta, we'll see that v plus is going to have an e to the minus alpha. So this is, notice that there's no j or I up here. And then e to the minus j beta z, thus why we call this beta, because it ends up being the beta like we had in our sinusoid, plus v minus e to the alpha z, oh, need a z here, e to the j beta z. So this is what our total solution looks like in phasor form. And this term here is just going to be the attenuation factor, right? So you can see that the signal is going to attenuate in terms of its amplitude as the wave travels in either the positive z or the negative z direction. One thing that might take a couple glances to understand is you see this e to the alpha z, and you might say, oh, well, isn't this blowing up? And the answer is that, don't forget, this is a wave traveling in the negative z direction. So while your eyes wander in the positive z direction, it looks like the wave is blowing up. But in reality, since the wave is propagating in the negative z direction, this e to the alpha z still indicates that the wave is decaying in amplitude as it travels. So to take the instantaneous form, remember what we do is we multiply by e to the j omega t, and then we take the real part. So when you take the real part, everything that's e to the j something goes inside a cosine, and then everything that's not just goes outside of the cosine and turns into the amplitude. So the instantaneous form is going to be, so now it's, there's no subscript z, and it's a function of z and t, is going to be equal to v plus e to the minus alpha z. I'll make that minus there, cosine of omega t minus beta z, plus v minus e to the alpha z cosine of omega t plus beta z. So that is what the instantaneous form of the solution to our lossy transmission line looks like. And again, now that it's in the instantaneous form, you can see more clearly that you have a sinusoid traveling in the positive and negative z direction, and they decay as a function of exponential of alpha z, negative alpha z in this case, and e to the alpha z in that case. So it kind of exponentially decays as it moves on. Now, to take a closer look at the characteristic impedance, what we're going to do is we're going to apply this Phasor form. So we're going to apply the Phasor form how we applied it to 3 and 4, and applied that d by dt is multiplying by a factor of j omega trig. If we apply that to equations 1 and 2, so if we analyze equations 1 and 2 by applying phasors, so applying this Vs is going to be positive e to the minus gamma z and e to the plus gamma z. You can plug this in, and then if you solve specifically for v plus over I plus, what are you going to end up getting? So again, you plug this in, compare the coefficients for v plus and the coefficients for I plus, and that is basically how you derive your expression for the characteristic impedance of the transmission line, right? So if you solve for that, you're going to get z naught, and then after quite a bit of math, you're going to find that z plus is going to be equal to r plus j omega l over g plus j omega c square root. So this is another quantity to keep in mind. And also, since these are complex numbers, you can also write the final result as a complex number, which is going to be z naught e to the j theta z. So we can also remember that no matter what this number ends up being, it's just another complex number. So you can also rewrite it in the form of some kind of amplitude, e to the j, some kind of phase. And that is very important because a lot of times when you're multiplying or dividing it by z naught, so thinking about it in terms of its polar coordinate forms is very helpful. Now, one last quantity that I want to introduce is just some general expressions beyond this for how to find alpha and beta. So if we take this expression and do the binomial expansion, for a few terms, and then do some comparisons to solve for alpha and beta. Another approximation that's good to know is that alpha is going to be equal to 1/2 of r square root c over l plus g square root l over c. And beta is going to be approximately equal to omega square root lc of 1 plus 1/8 g over omega c minus r over omega l squared. So if you're just looking for a numerical value for the real and imaginary parts of gamma, and you don't have a fancy calculator, you can just type this in and have it automatically organized into real and imaginary parts, you can use this expression to somewhat approximate it. And the other thing to remember is that for the lossless case, so if r and g are both equal to 0, you should have you will get alpha is going to be equal to 0 because both of these terms are going to be 0. And separately, you have your basic definition of beta, which is omega square root LC. Remember, square root of LC is 1 over Vp, so it's also 1 over the phase velocity, what we were describing earlier. So also know that this is the expression for alpha and beta in the case of a lossless transmission line. So to summarize, we start out with our basic equations, transmission line equations, by using Kirchhoff's voltage law and Kirchhoff's current law for this layout here. You get these differential equations. Through some fancy substitutions, you get these second order differential equations that just have one variable. We rewrote our instantaneous form into a phasor formation, and then also used the fact that a derivative with respect to time is just multiplying it by j omega. So that turns this into a polynomial, which allowed us to do some fancy reorganizing. But the bottom line is that the second derivative with respect to z is going to be equal to some complex number squared times vs. And that complex number, if we separate it into a real part and an imaginary part, the imaginary part ends up being our beta, and then the real part is our attenuation constant. We can then convert that back into instantaneous form, and you can see the sinusoid, traveling wave sinusoid with exponential decay in both directions. And then by looking at these first two equations, we also have an expression that we can get for z naught. But basically the take home is that if you know what these values are, z naught is going to have complex magnitude and angle. If it turns out that you have this L and C, that means that your characteristic impedance now has a phase angle associated with it. And then we also had some approximations for alpha and beta if you didn't want to just punch this in with a fancy calculator. And remember that in the lossless case, alpha is equal to 0, and the definition for beta is omega square root LC. So for the next few sections, we're going to use these as the basics for analyzing different aspects of a basic transmission line setup.